I am Arje Nachman, and I manage a portfolio in electromagnetics. I've done for a long time. And here's the sort of, as they say, brief description of the portfolio. It's the interrogation of Maxwell's equations, both linear and nonlinear, and the sub-areas, four that are sort of generally capture most of what I fund. Theoretical nonlinear optics, wave propagation through complex media, fundamentals of antenna design and operation, and fundamentals of EM exposure on circuitry. And I should say that the first and the fourth sub-area have their own annual contractors meeting, and that's because they concern themselves with things that are sort of have little intersection with anybody else. And the middle two are linear Maxwell's equations, and they don't know they've been broken up this way. I know they've been broken up this way, but they get together at an annual contractors meeting and discuss the results of their research. So let me go through all four of them a little bit to give you some idea of why I'm doing it and what's going on. This first one, complex media as I define it here, actually I've defined it again here, but complex media as I define it here is media that nature gives us. And I really own this area. I funded it. I fund it because the Air Force is obliged to deal with, in other words, to do imaging of one kind or another, whether it's radar or laser or what have you, through media such as clouds, the walls of buildings, soil in some instances, and well, even possibly the ionosphere. And every one of those examples, and foliage, every one of those examples is dispersive and some very worse. And the ionosphere is all of these things. And so the question is, can we help the Air Force do this by casting a wider net, or thinking out of the box maybe, and find a class of waveforms, which are called precursors, that have the strong potential to upgrade the imaging quality through them. And as you'll see some slides from now, what I mean by these kind of class of waveforms are actually time domain solutions to Maxwell's equations. I'm absolutely convinced that in most circumstances, certainly in dispersive media, that CW, which is basically an infinite sine wave that runs forever, which is what the Air Force uses, both in LADAR and in radar, is not the right answer, and I'd hope to convince you to adopt my position on that. Antenna design and operation. So I've written that suitable partnerships of materials and geometry can deliver man-made composites, man-made, which exhibit novel EM attributes. And before I get into this, well, let me just say that examples of metamaterials are negative index materials. That's the area that popped up not so long ago and basically is the source of the term metamaterials. But I cast a wider net, and I include photonic bandgap materials and something else I funded a few years ago, unidirectional composites. And one of the reasons that we're interested in this, among others, is that reliance on small UAVs drives the need to miniaturize antennas, make them more responsive, and one way of doing that is to see if you can make them out of some of these novel composite materials. However, up here, it's classically been felt that dispersion is a material property. Water is dispersive, so is glass, and a lot of other things. However, in fact, a more accurate definition of dispersion is when the wave propagation through the media depends on the frequency that happens to be there. And every one of these things here enjoys or suffers from that situation. Negative index materials are only negative in a very narrow band gap. They're generally made by, in some instances, by distributing spheres of one material onto a lattice of air, for example. And it's at certain wavelengths, that effective media behaves as if it were made out of something that had negative permittivity and negative permeability, I mean, even though it's not. The constituents don't have negative permittivity or negative permeability, but the effective media does. And how does that happen? That happens because the geometry produces some scattering, destructive and constructive interference, which renders the material as a negative index material in a very narrow window. The same thing happens here. Photonic band gaps are regions, are materials, or structures made out of two or more constituents. Each of them are basically transparent to almost all frequencies. When you construct a structure out of them in the right way, they all of a sudden are opaque to certain frequencies. That's why they're called photonic band gap. In other frequencies, they're still transparent. And the same thing here. So it turns out that it's an important realization that dispersion has two parents. One of them is material. The other one is geometry. And you can find instances when they conspire to, even here, they conspire to produce a very interesting responses to waveforms. Not all of my antenna design and operation is worrying about metamaterials. Don Hearn talked, was it yesterday, I guess, that I handed off a problem to him that had come from one of my lab tasks at the Sensors Directorate. It was a problem that in phased array radars, the phased array radar is just a huge checkerboard. Instead of being 8 by 8, it could be 1,000 by 1,000. And phased arrays run by doing phase shifting on each one of those little squares. If you do it right, the beam does this without any physical motion because of constructive interference. But the phase shifters are very costly, and if you have 1 million of them, you can't afford to launch such a thing into space. So the people at the Sensors Directorate said maybe we could run 8 or 10 of them together, so you can cut the cost by a factor of 8 or 10. The question is, which 8 or 10 should you do, and how do you cover the thing? If you do it in bricks, you ruin things. If you make it random, you can get rid of some of the bad effects and keep the good ones. And so the Hanscom people speculated that polyominoes are a good thing to do. I knew nothing about that. I don't know that community. So I went straight to Don. So that's another example of this business of antenna design and operation, which I haven't mentioned there, but it's in the background. Okay. The other two of my 4, nonlinear optics. So I'm interested in for example, in this business of femtosecond pulses of IR lasers. In 1996, 95, something like that, the Europeans reported that when they produced a pulse whose center frequency was in the IR and whose duration was 50 femtoseconds, it would produce something that was the diameter of a 50-cent piece, very thin, of course, and that thing traveled through the air without diffracting. And one of the people I was funding at Arizona called me up and told me about this. I had visions of solitons. It turns out it's not, but nevertheless, the modeling of that comes from nonlinear Maxwell's equations. It is nonlinear partial differential equations. I'm going to talk about a little bit about that later. And I also fund a great deal of work in solid-state lasers. They sometimes really are solitons. In fact, the communications community wanted to use solitons in optical fibers for years. But we want to use them to produce basically fiber lasers. And the question is, can you get away from the mindset that to design fiber lasers to avoid nonlinearity everybody keeps trying to do that, and my suspicions are that there's something to be gained if you don't, and if actually try to get it to work on your behalf. The RF effects on circuitry is a little part of my portfolio, but an interesting one. The whole point of it is to identify waveforms which produce various circuit upset mischief on somebody else's circuit. It's a form of electronic warfare. And the reason that we think it can be done is because everybody else's circuits, whether you're guidance on upcoming missiles or somebody else's laptop, they all have transistors in them. Transistors are nonlinear circuit elements. That means that they can be subject to becoming chaotic. If you poke them the right way, we don't know yet how to poke them, but that's what we're trying to do. And we're trying to keep away from, as near as I can tell, the business of trying to burn them out by high-power microwaves. If you could do that, fine. Then you don't need me, and you don't need any sophistication except for designing the high-power microwave source. Then you could talk to John Lugan's land. The question here is whether you can do waveforms that actually an airplane with a regular radar can produce and affect something like an upcoming missile and cause it to go deaf, dumb, and blind by doing something sophisticated. We don't know how to do that, but that is what we're trying to do. But this is complicated by the fact, something I learned recently at the contractors review, that some of these effects are dictated by the activity of the item at the moment you're doing it. So the computer you're trying to mess around with, it makes a difference whether it's running a PowerPoint things or email or this or that or the other. I had no idea that was the case. Now I do. I think it's a fascinating situation. In other words, but anyway, the whole point of that business is to try to find suitable waveforms that act at a distance to do what presumably would be temporary upset, but in some instances that's all you need. Okay, I thought it was important for me to mention the impact of MURIs on my program. They're huge. I have one of my own, although I share it with one of our new program managers, going to talk later today, tomorrow. Anyway, Rick Parra speaking. He's a co-program manager on this thing. But I have a MURI on these ultra-short laser pulses, which I just described. It's a very interesting thing. And I'm going to describe it in the next couple of slides. And there are two more MURIs that are supportive of my of this area wave propagation through complex media. The second one is something I am a co-program manager on with John Lugan's land, and he mentioned it in his talk, this high-power, low-loss artificial materials for transformational electromagnetics. That's just a fancy way to name for, can you design high-power microwave sources by exploiting whether something inside of them might be made out of some of these metamaterials that I mentioned on the other slide. Right now, they're not. Deep optical turbulence is something I'm not a program manager on. This is owned completely by Kent Miller, and he mentioned it. This is basically the question of propagation of various beams and so forth through atmospheric turbulence. Nevertheless, success in either of these things is going to be important to my program. So I think it's something that bears mentioning in this talk. Now here's a chart that Jerry Maloney made for me, except I put down a little bit more in it. But this is his MURI. So this is the main university, University of Arizona. Here's several universities down here that are players. This one, of course, gets no money from it. They can't by law. But Pat Roach is a lab task at RD who does some experiments in this area. And this lab task is not mine. It's Dr. Parra's, and I assume he'll mention it. I don't know. But this is a very distinguished group of people. Nicholas Bloombergen is a Nobel laureate who retired from Harvard, came to Tucson where it's warm. So he putters around there. He's 90, but there he is. And if you paid any attention at all to Dr. Carrick's talk on Monday, he had a slide where he had all sorts of winners of various and sundry awards, and one of them was that the president nominated a AFOSR PI, or AFOSR supportive a woman to be the chair of the Medal of Science panel that awards those things. That's Margaret Murnane, and she was on our Hall TV at one time. Okay, now I want to do just one slide on what they're doing in this area. Let me give you a little background information. As I said, this thing was first done in Europe They're way ahead of us on experiment, but we are the leader in the world on modeling and simulation, and I like to think that's because of me, and I've been funding this, as I said, since the middle 90s, but only recently got a MURI in it. But these little pulses propagate through air without diffraction, and when they do that, they ionize the air. One of the reasons that I was so amazed when I heard about this back in 95 or 96 was the very idea that air could be a nonlinear media. I had been used for a long time to think that optical fibers are nonlinear media, and you could get solitons in them. But when I heard that air was a nonlinear medium, I was really surprised. However, I really shouldn't have been. There's no such thing as a linear or a nonlinear media. If the intensity of the electromagnetic field is high enough in the media is nonlinear. And so you're the one who decides whether the media is nonlinear, and it doesn't. And air, like anything else, the index of refraction of air is N0, which is a constant, plus N1I. Intensity, I, is E squared. And then there's higher terms. And when you stick that into the Maxwell's equations, you get nonlinear partial differential equations, and air can be a nonlinear media. So these little pulses, these little disks, propagate and ionize the air as they go. The fact that they're 50 femtoseconds in duration is very important, because if the power in that little disk is 4 to 20 terawatts, and if that sat around for longer, then it would produce its own thermal blooming and stop itself. So the first nonlinearity that anybody ever knew about was basically thermal blooming, and it was a bad one. But these little pulses go so fast, they're gone before the air can heat up. And they do ionize the air as they travel along. And that means that when you model the whole thing, you have to model the plasma formation as part of the modeling of the entire process. And for a while, people were doing the standard thing. They had an equation for the electromagnetic field, and then a Drude model for the electron population. But that wasn't doing so well, and they think they understand why. What they think is that when the electrons are first ripped off the molecules in air, they don't form a legitimate plasma. And what they really do is, if you look at this carefully, you see a bunch of wavy curves, and finally this red one, which encloses a yellow area. All of those curves are curves of the electron distribution. Only the yellow one, which is covered by a red line, is the Fermi-Dirac distribution. And that's the long time. It takes about a picosecond, because when you first start out, the A curve, which is, I guess, the one the furthest to the left, is a non is early time distribution of the electron momentum. It is not a legitimate plasma. And Dr. Maloney has this. I decided to keep this. This is not my terminology. It's his. It's a new state of matter. I think that's wishful thinking, but it's certainly good for public relations, I suppose. But in other words, it takes about a peak. The electrons are not in a state where they get described by the Fermi-Dirac distribution. This, however, all of these curves are done by simulation. This is an experiment. I don't know what the experiment would be to do that. In order to do this, they had to use the quantum Boltzmann equation, which is a many-body equation, which is all Boltzmann equations are many-body equations, and they produce all of these curves, including the very last one. So this is a simulation. It's the kind of stuff that I understand. If there's ever an experiment to show this, then Dr. Pera can tell you about it, because I won't be able to. And Dr. Pera has his own slide that Arizona gave him for the MURI. It's a different stuff. It is experiment, and he can take you through it, thank God, because I don't understand it at all. Okay. Now let me get to one of my main stories, which is this business about precursors. The story of this is kind of interesting, and if I go back to tell you the history, it's a good instance of the serendipity of science. Many years ago, I was asked by Armstrong Lab, which is currently the RH, Human Effectiveness, to look at the question of very short pulses, which were produced by radar technicians when they were turning on and off the radars on parked airplanes, on parked F-15s and parked F-16s, to look into the question as to whether these transients that they produced were really harmful. because the health and safety people used health and safety rules that were based on an analysis of CW, which is basically sine waves that go on forever, and those things stop at the chest wall. Transients is no such thing, and so we started funding this kind of business, and back in those days, this business, water was in fact it. The human body is 98% water, so we decided what happens if we take a very short, take a short pulse, which is very draconianly modulated. In this case, it's a square wave modulated pulse, and send it into this medium. And what you get is this and this. Each one of these is the precursor. It's a kind of a bump, has some wiggles in it. And for the human body, that means that what the radar technicians were doing would come out their back. It didn't stop at the chest wall. These things here, it's important for me to say that we produce this, the media produces this. It resculpts the incoming wave all by itself. It likes precursors, and the reason I know it likes precursors is because the precursor decays, this maximum amplitude decays as the 1 over the square root of the distance into the medium. And it contains quite a bit of bandwidth. If this box weren't here, and if this were a sine wave that went forever, these things would be decaying exponentially with depth. For a long time, I funded it. I regarded it as an interesting thing. They reported it, to the Surgeon General. I don't know where else it went. But it took me a while to realize that this was telling me something very, very important about dispersive media. And in fact, it was this incoming wave, rather than a CW, which caused the media to tell on itself, to describe something about itself that no one ever suspected was the case. That there are certain waveforms that propagate in a way that sends them deep into the media, and they're not monofrequency. Like, well, this isn't either. Anything. This thing has an infinite spectral content because of the sidewalls, because of the vertical jumps in the thing. And we started thinking that maybe whether there may be lots of media that are water-like, but let me see one more thing. And just to give you an indication of what had to be, those precursors are exact solutions to Maxwell's equations. This is a transform version of it. This is water. This is the index of refraction. This is was made up by the physicist Lorentz. It's causal, so you have to use something that you trust. And it does predict exactly what I said. It predicts that the wave has a 1 over square root of z behavior. And you just have to go through the mathematics very carefully. I don't intend to do so. But I exhibit this because I wanted people to see that these sorts of results are done by almost pencil and paper. You have to be very, very careful. This thing here is kind of a Laplace Fourier transform, and it can't be found in any compendium. You have to do it yourself. You have to. It's what's called a Bromwich path contour in the complex omega plane. Blah blah blah. If you have never seen that before, then. So later on, it occurred to me that another interesting science question was, would sparse discrete media support precursors? And that's a model for clouds. They're the little water spheres. And so this is no longer a continuum, a half space of just blue, and that's why I made that long talk about the geometry plays its own role in producing dispersion. What's inside of these spheres is water. It's materially dispersive. But a random collection of scatterers is also dispersive, and in fact, while I'm going to show you results that apply to these water spheres, the Dr. Elizabeth and Marek Blazinski did the same thing for dust. They're impenetrable, they do support precursors, and they do so because of geometry. Okay, so the question I posed was, can you do that? Now, this problem cannot be done pencil and paper. you have to do the Me series, which is one of the few exact solutions of Maxwell's equations. It's for scattering from a sphere, penetrable or not. And you have to do tens of thousands of them and lots of times, to do an ensemble average. And these people, the Brzezinskis, are superb numerical analysts. So they did this problem. They sent this pulse. Now this thing is in the 30 terahertz. It's the same. It's an IR pulse. It's the same frequency as lasers that the Air Force tries to use to look through clouds, mostly unsuccessfully. But this time we're going to do a square wave modulation. You got 60 cycles inside of there. It's important that the size of the droplets and everything are sort of more or less, or sort of half the wavelength of the thing. All of that's important, or none of this would happen. And here's what they found: precursors. Here's one at z equal to 100, and z equal to 200, and then I guess the green one, which you can barely see, is 300. It gets smaller by 1 over the square root of distance, as it should. This is a little cleaner than those wiggly bumps I showed earlier, but they are precursors. And what's happening in the clouds is that the cloud does a very interesting thing. Here's the original spectrum. It's peaked at 30 terahertz. And it of course has a lot of spectral content. But as you go deeper into the medium, for example, this is what happens with the carrier frequency, the 30 terahertz. It's almost not there, but these side bands are there, and they're very strong. So what happens is that the transmitted pulse has a significant amount of low-frequency components. The cloud strips out the 30 terahertz, one way, both by basically heating up the droplets a little bit and also by scattering them away. But the low-frequency part of the spectrum is only weakly attenuated, and it's around 220 gigahertz. And that's what these things are around. These precursors are around 220 gigahertz. So it makes its way. That's what comes out at the bottom of the cloud, but a lot of them. No longer ballistic photons, which is just a few that manage to miss every raindrop in the cloud, but this is a huge number of them. However, as I said, what's coming out is no longer has the spatial resolution of 30 terahertz. That's a very small wavelength, so you get very precise spatial resolution if you're lucky enough to get any of it through. This thing has are much longer wavelengths, so you've lost some of the good that the 30 terahertz would have given you had you been able to get it through in the first place. So the question, and oh, by the way, some of this initial part of this work, some of the seed money was given by DARPA by Dr. Jennifer Ricklin, and now she's going to see what finally came of this. So the question is, how do you get back some of the spatial resolution that you've lost when you've stripped out the 30 terahertz signal? And she's got this fabulous answer that she absolutely floored me with. Here's a sequence of these 30 terahertz pulses, and of course you need a sequence to get a lot of energy, a lot of feedback back to your thing. And what she argued was that between each pulse is a little dead space, and what she wants to do is make each little dead space longer than the last. That in itself is a modulation, and modulations add bandwidth. So by doing nothing, you get a lot. Doing nothing successively longer times, you get an increased spatial resolution of the target. And I should say now, this idea of hers has got nothing to do with clouds, nothing to do with IR lasers. This could be done with regular radar. And the modulation wouldn't be square wave, it would be very gentle. This interesting quiet space between pulses can be used for everything, and it'll increase your bandwidth. It can be done right now if the F-15 and F-16 pilots wanted to do it. But anyway, what you get out of the bottom of the cloud is a sequence of precursors. As they said, a train of them. They're sequentially also further apart, and they do give you a lot of, here's the bandwidth, here's the difference between the maximum and minimum of the wavelength. So this is so let me sort of produce a summary at my own risk, I guess. So for microwave radar imaging, we can't get, well, we can, but it's difficult to produce square wave modulated signs. But it turns out a radar can produce precursors all by itself. That can be done. These things contain a greater bandwidth than narrowband. They decay algebraically. When they hit an interface, they produce, if they're matched to the medium, in other words, in the other side of the medium is water, and the water already likes them, you get much less of a flash, what's called a treetop flash sometimes. And if you make the match filtering, it makes it easier. If you send in something that's going to come back to you, then the match filtering is easier. And it's not, none of this is seriously modified by oblique incidences. The problem I found, I showed you was normal incidences. It doesn't matter. You get precursors anyway. For imaging through clouds, it's very easy to produce square wave modulated sinusoids. You have to turn the laser on and off very quickly. It can't produce precursors by itself, these little IR lasers. The cloud produces a precursor, just like the water did when we first did it. And in order to compensate for the loss of the higher IR frequencies, we do this interesting pulse train modulation. Okay. Lots of people have mentioned wave propagation through turbulent media. So I found a little bit of that. This started years ago when Air Force Material Command got up some interest in using lasers as part of a communication net, not just radios. And so they concocted some program called TCATS, I think, and I've forgotten what it stood for, Transformational Communication something. And I started getting interested in this. And so the question is, that, as we all know, the optical beams are hindered by atmospheric turbulence, random fluctuations, et cetera, et cetera. And these free space optical communications are certainly adversely affected. This is an old example, this is a mirage, but it is one. But this is more germane. This is how the laser beam is distorted by turbulence. And back then, I was funding Emil Wolf, who's the famous Wolf of Born in Wolf fame. He's still alive. I still fund him. He's 87 or something. But he came up with this idea that while a coherent laser is going to get screwed around and possibly miss the target, if you do a partially coherent ensemble of beams, you might win. Sounds like a simple idea, and I subsequently funded one of his young postdocs, Greg Gabor. I thought I had written his name someplace, to look into this business of finding what sorts of partially coherent choices you might make, and he came up with an interesting one. And these are Airy beams. Airy beams are beams that they don't curve, but something does. I'll tell you in a second. But the question is that you might be able to get yourself from there to here. This picture is sort of a 3.5 kilometer, distance, and they might be robust enough to do what you want. You can make Airy beams by running a regular beam through an appropriate phase mask. You need a cubic phase distribution. The Airy beams, they don't really propagate in a curved path. Everything propagates straight. What's propagating in a curved path is the brightest spot. It keeps diffracting this way because of that cubic. So the brightest spot looks like it's propagated along a curved path. It hasn't. Effectively, it has. When these things first came out in the medium, reporters were running around telling we could look around corners. You can't. If this thing hits something around a corner, the magic is instantly destroyed. It doesn't come back around the corner either. So that's nonsense. But these things but for this purposes, you might actually get away with it. And what's really interesting about this idea that Greg Gabor did is that he discovered that 4 picture that I showed is better than you think. 4 beams is enough. You don't get much better with hundreds of them. You get all the scintillation minimum that you could possibly want with 4 beams. So this is, and by the way, that circle that I had back there, that's about 10. It's less than a foot across. The circle that those 4 are sitting on is about 10 inches across. So these things can be easily to do. So other things you could do. So additional beamlets are not diverse or don't add anything. They're a waste of time. We haven't looked at the business of polarization, but that's another idea. So, okay. Now here's I think an interesting sort of a boutique thing I'm doing in nonlinear optics. It's imaging. So this is Jason Fleischer. He's at Princeton. First of all, I've written here what it called the classical nonlinear Schrodinger equation. It has a linear part, this and this. It has this nonlinear part, which multiplies psi. And the question is, so what? And I'm going to go back to this slide in a minute, but let's take a look at this slide here. In a conventional imaging system where you have a lens, if you have some screen that blocks any of the rays, it's irretrievable. Whatever comes to the focal plane, if it's missing information, you can't get it back because of the linearity. And Dr. Fleischer has had an interesting idea. He said, instead of this lens, let's put a nonlinear crystal in here. What will that do? Well, some of you know or have been told that with nonlinearity, you get frequency sums and differences, second higher harmonic generation, all that kind of thing. It turns out that you get that sums and differences of frequencies also happens to the wave number vector. You get vector sums and differences. And what that means is that what comes through here, even if it looks like it's going to be cut off, part of that has been summed already into something else, and all of the k's arrive at the focal plane, but not as they were in the image. They get schmoozed around. So you get a mess. Nevertheless, you've retained all this information thanks to nonlinearity. So what do you do with this information? You emulate the crystal this way with a nonlinear Schrodinger equation. This is a spatial version of time reversal. And so what you get when you go back this way is the picture that was there before it got messed around by anybody. And so what you get here is this. Those of you can see on top of here, there's 4 orange bars and a blue one. The blue one disappeared from here, and you can never get it back because the information isn't there. This blue one appears after the nonlinear Schrodinger signal processing that it does. It sort of undoes what the crystal did, but you had to have the crystal there in the first place to give you a focal plane picture that had all those k's in it. So this is an interesting idea about how to do nonlinearity for imaging. I'm going to skip this thing. That was just a photonic band gap. And I want to go into this one. I hope I have time for all of this. This is interesting stuff. Back in 1998, Carl Bender and his co-author published a paper to answer a question, can a non-Hermitian operator exhibit real spectra? And this is for the Schrodinger equation. And the answer turned out to be yes. That you can get real spectra out of this equation, provided that the Hamiltonian commuted with parity in time, which means that if you changed space and changed time, nothing happened. The eigenvalues that you get from a v equal x squared, which is a standard quantum mechanical oscillator, and the eigenvalues you get for v equal ix cubed are the same. The eigenfunctions are not, but the eigenvalues are, and that's the only question they wanted to answer. Can you get real spectra out of bizarre Hamiltonians? Well, so what? I read this paper a couple of years after it came out. I had fun reading it. I didn't think much about it. But fortunately, 2 guys who were smarter than me did think much about it. Professor Christodoulides, well, I guess it's on the next slide, and Professor Kotos. And they noticed the following thing. This Schrodinger equation is identical to the periaxial approximation of Maxwell's equations. The only difference here, what stands here with the potential, now you have the index of refraction. And the index of refraction can have, a complex index of refraction can have a real part, that's a real index, and an imaginary part, that's gain and loss. And so it's possible that if the index of refraction did the same thing as V, you could get real eigenvalues out of that. And why do you care? You care because 2 waveguides like this next to each other, if you put a chromium bar up here, which is a source of loss, you get less and less light coming out of the left waveguide until you get to here, and then you get more. It actually, an increase of loss will give you more waves, and so if you're down here, you can go either way and get an increase. Do I stop? You're out of time. Okay.